are looking at the space Ben-Zvi X, the space of G bundles on a Riemann surface X, and we are trying to construct some correspondences on it. So before we got carried away with these derived categories of D modules, we were trying to do something very geometric. Let me just remind you that if you have we said if you have a space X with a G action, which you can write in terms of these two projection maps, you have a projection from X, there's a projection and there's an action map, then we got a certain correspondence over the quotient X mod K, which was given by X with some G mod K over X mod K. So there was some projection like this, and this is a projection where the fibers of these maps look like the double cosets of G, double cosets of G with respect to K. So we have the space Ben-Zvi of X, and what we're going to do is we're going to construct, because we've seen that this space has a huge amount of symmetry. Nothing is really acting on this space, but it came as a double quotient of some gigantic groups, which means that we're going to have lots and lots of interesting correspondences on this space. So let's write down what these correspondences are. So we want to write this down very concretely. So what is the correspondence I'm going to do? My group, I'm looking at the space Ben-Zvi X, and there's a natural correspondence to write with, I'll call Hecke, let me call it Hecke sub X. And so this is going to be a natural correspondence over Ben-Zvi X, and it's given by this picture. So what am I going to do? I'm going to take a G bundle. I'm going to remember that I got this G bundle from something that it had a trivialization at the point X. I can choose a trivialization at the point X. Then I can change the trivialization at the point X. And then I get another G bundle. And then I forget the trivialization. So what does this mean? Concretely, this means we look at the correspondence, which is the pairs of P1 and P2, pairs of G bundle here, a G bundle here, plus the following data. We have, let me not give it a letter. We have an isomorphism between P1 on the punctured Riemann surface and P2 on the punctured Riemann surface. So what does this say? We're looking at pairs of G bundles where the only thing that varied from one to the other is at the point X. So I claim this is exactly the correspondence you'll get by applying to this double quotient description that I had before, where my group K here, so my group, this is the loop group, and the positive half of the loop group is now playing the role that we had here of G mod K mod K. So for every point in X, we get this correspondence. We get the space of triples, a bundle, another bundle, and an identification between the two away from the point. So let me just, let's see what this does. First of all, let's just point out, in the case of GL1, what does this thing do? Well, we have pick X, we have pick X, and we're looking at pairs of line bundles, L1 and L2, and they're identified away from a single point. So how can I change a line bundle only at a single point? That just means, if I think in terms of divisors, I've just changed the multiplicity of that point and its divisor. So there's basically Z ways of doing this. This is going to be pick X cross Z. So I can think of it as the collection. We have L1 and L2, which is L1 of some multiple n times x, where n is an integer. So this is what this correspondence looks like. And in fact, what is this map here? This is just the graph of the action map. Z is a group. It acts on pick by adding something to the divisor at x. And this is just pick x acting. This is just the action map. Great. So that's all this Hecke correspondence is in GL1. It's just this correspondence is what's left of the action of Z on the Picard group. Okay. No, I'm working in an algebraic setting. I'm not claiming I can choose a trivialization away from a single point. I'm just looking at pairs of bundles that happen to be identified away from this point. I'm not claiming that any two bundles are isomorphic away from a point. Just looking at such data. So the idea is that now what has replaced Z? What has replaced Z? So let's look at the fibers of Hecke of this correspondence. Well, this is going to be the same picture as in the general case. The fibers of them are going to look like the double cosets. So that's a general statement. In our case, if you look at the fiber, for example, over P2 equals the trivial bundle, let's suppose P2 is trivial, then this is just, what is this? This is G bundles P plus a trivialization on X away from X. So what does this set look like? You have a bundle, and you've trivialized it. This is the identification with the trivial bundle on the complement of a point. So what is the data that's defining such a P? To define such a P, all you need to give is a single. So here's my bundle P. It happens to be trivialized on the complement of this point. Now, I'm not saying every bundle is trivializable. I'm just looking at these ones. So you have a bundle trivialized away from a point. So you might as well pick a trivialization also on this disk and then get rid of it. So what you get, that this space is isomorphic to LG mod LG plus. This is the affine Grassmannian. In fact, it's completely independent of the curve X. All of the data to describe a bundle with a trivialization on X away from X is completely local. I choose an extra trivialization near X, I get a transition function, and then I forget about that choice of trivialization. So I think I misspoke. The fibers here are G mod case, right? Not K mod G mod case. So the fibers, so this fibration of Hecke over ether factor, the fibers look like this affine Grassmannian. So the affine Grassmannian is now our analog of Z, as we said before. But the natural algebra that we're going to look at is if we want to construct an algebra, we need to look at something like functions or K-classes or sheaves on double cosets. Those are the things that are going to act. OK, so in other words, this is one way to say this is that Hecke X mapping to Bun G is Gur bundle with structure group LG plus. So that's kind of the shape of this over one of the factors. OK, so this is what the space looks like. So now what we need to decide is what we can do with this. Well, in the abelian case, this LG plus, this Grassmannian was just a bunch of components, a bunch of Z's. And we knew how they acted. You could take a line bundle and modify it by n times a point for any n. So in the case of the Grassmannian, you don't have this. This Grassmannian is not a discrete object. But let's say, for example, in the case of GLN, what kind of modifications can you do? How do you modify a bundle at a point? And let me just give some examples. They're so-called elementary modifications. So we have elementary modifications. So if I want to take a vector bundle V in Bun N, and I want to modify it at a single point, one thing I could do is I can pick an integer that's between k and n, and I can look at a piece of this big Grassmannian, which is just look at V plus k dimensional subspace of the fiber V at X. one thing I can do is pick a k-dimensional subspace of the fiber V at X, and then I can, let's call it subspace W, and this again maps to Bun N of X. These are the elementary modifications. I can look at the sections. There's a new vector bundle defined by sections of V that passing through this particular subspace W at the point X. So make the restriction on the sections. So this defines a new vector bundle whose sections are forced to lie in this particular subspace at X. So this is an example of a modification. These two bundles are exactly the same away from the point, but I've changed them in the point. But the point is that this is a correspondence. I don't have a canonical choice of subspace. The fibers of this map are exactly Grassmannian of k-planes in Cn. I mean, they look like Grassmannian k-planes in the fiber of V. So this is a piece of this affine Grassmannian, are usual Grassmannians. Okay. So these are called, and these pieces are going to correspond. These will be certain closed LG plus orbits in the Grassmannian. So rather than looking at the Grassmannian for GL1, which is just a discrete set of points, and our natural correspondence were labeled by components here, now we're just going to look at certain orbits. For example, these are closed orbits in this Grassmannian, which happen to be isomorphic to finite dimensional Grassmannians. Let me just note in passing that the cohomology of the Grassmannian has nothing to do with anything right now, but let's note that the cohomology of the Grassmannian is isomorphic to the kth exterior power of the n-dimensional representation of GLN. Just a cool fact. Now, so the claim is that these elementary modifications will generate all the Hecke correspondences in the case of GLN. But in other groups, we're not going to have such a simple description. So let's think a little more. So now I want to just think a little bit what the affine Grassmannian looks like. So let's just look at the affine Grassmannian, because that's kind of our fundamental local data. And let's think what it looks like. So again, I'm going to focus on GLN first. So we're looking at LG mod LG plus, where you take your, I guess the plus seems to migrate, where this is GLN of Laurent series mod GLN of Taylor series. Now, what is that space parameterized? Why is it called a Grassmannian? So a nice exercise, you need to find some set on which this thing acts transitively with stabilizer this, and there's a natural such set, which is, if I look at lattices, so I look at subspace lattices, so these are subspaces in Laurent series of Z, n copies. I take an n-dimensional vector space over this field, and I look at subspaces of it, which are lattices, means these are going to be subspaces that are preserved by multiplication by Z, and also I want them to have an appropriate size. I can't say, I don't want them to be finite dimensional, so I can't say the Grassmannian of k-planes, but I want them to be commensurable. I want them to be of a certain size. I want them to be of the size of the positive half. So look at subspaces that look like the positive half, and it's an easy exercise. The GLN acts transitively on these, and the stabilizer is exactly GLN of Taylor series. So this is a description of this space. And so now what does this space look like? Well, the space is a union. It's an infinite dimensional space, but it's a union of finite dimensional orbits. This again is going to be true for any group. It's a union of finite dimensional orbits for the group LG plus. For example, it has a base point which is fixed by LG plus, and every other orbit differs by it by a finite amount. So these are all finite dimensional orbits. But it's not going to be enough for us to just say it is a union of finite dimensional orbits. I want to say, what are the actual orbits? What do the orbits look like? So let's try to describe what are the orbits. In other words, what are the double cosets? What's the set of orbit look like? Well, what are we doing? We're looking at GLN, Laurent series in Z. So we're looking at n by n invertible matrices of Laurent series. And we're doing to them row and column operations. So this is linear algebra. We're doing row and column operations by matrices that are not allowed to have any poles, and matrices, in fact, that have to be invertible over Taylor series. So what does that give me? Well, if I'm allowed to do row and Taylor operations, I can always take this matrix, and I'm going to be able to diagonalize it. It's an invertible matrix. I might as well bring in diagonal form. And moreover, once I have it in diagonal form, I'm not going to be able to change the orders of the Laurent series I get along the diagonal, but I am going to be able to get rid of everything but the leading coefficient. So I'm going to be able to bring this to the form z to the k1, z to the k2, z to the kn, any matrix up to row and column operations, I'll be able to bring in this form, and I can even choose to order these things. Okay? So this gives me a description. This is the normal form for these double cosets. So the double cosets are labeled are exactly given by this. You take the double coset of this matrix, and every matrix can be brought into that normal form. Okay, how does this work so this set might look familiar from various ways, but let's just make sure we don't get it wrong. Let's see how would this work for a general group G. So for a general group G, what are we doing? Let's say the same words for any group. So for general G, what is mean diagonalization? I'm going to pick a maximal torus in G. And now what is the analog of these matrices, z to the k1 up to z to the kn? These are particular Laurent series in G, but they're actually diagonal Laurent series. They're Laurent series in T. And in fact, they're not just Laurent series in T, they're co-characters. So I can look at homomorphisms, group homomorphisms, from C star into T. And that's what these guys are. Now I'm going to think of this as a function of Z. These matrices are homomorphisms from C star into diagonal matrices. So what I'm giving is this lattice lambda, which is the co-character lattice. Lattice. That's the definition. And the point is that if I give you lambda in the co-character lattice, I can now think of it as forget about the fact that you have all of C star. You can think of it just as a Laurent series in T. So you can think of this as a subspace of T over Laurent series. Lambda gives me a particular Laurent series in T. Just look at it near the origin. And I can look at the double coset of lambda in the Grassmannian. So for every co-character, I get a double coset. And now we don't get, these are not all distinct. No, here I had to order the double cosets. I had to put these k's in order. So here, what I find is that I get a bijection between double cosets and co-characters up to ordering, which is the Val group. So W here is the Val group of G. So this is a general description. The set of double cosets, these are all finite dimensional orbits of LG plus on LG mod LG plus, and they're labeled exactly by this set. Okay. So what do we do with this set? So now the point is that this set, lambda mod W, has several ways. We can think of it in different ways. So we can think of lambda mod W the following way. I'm going to think of lambda, these co-characters, I'm going to think of them as characters of the dual torus. These are characters of the dual torus. We take the torus T and we define the dual torus, which is essentially defined so that this is true. Okay. So we take a torus whose characters, the homomorphisms to C star, are exactly given by the co-characters of my original torus. So this defines me a new torus. So now what is lambda mod W? Well, we have a torus, and we're looking at characters of this torus up to a Val group. So we can think of these as dominant characters, or if we like our highest weight theory, we can think of these as irreducible representations of a reductive group So if we had a nice reductive group with maximal torus T, with maximal torus T check, torus T check. So if we have a reductive group with maximal torus T check, then its irreducible finite dimensional representations are exactly given by characters by highest weights, which are W orbits of this form. So we're going to look for a group G checks. The idea is that, and what we find is that these orbits, so just to summarize, is that our double cosets are in bijection with irreducible representations of some group G check. Now, this group G check here is kind of has not even been constructed yet. It's just been suggested purely combinatorially. We're just saying that if you look at the set, well, in the case of GLN, this set n tuples of integers, this you can think of this as also the set of data that labels irreducible representations of GLN itself. The maximal torus of GLN is C star to the n, and it's self-dual. So we could have identified, we could have gotten this wrong and missed the duality. In general, we notice that this is not irreducible characters of our group, but of something dual. So now we can introduce a gadget, and it's right now it appears as a purely kind of formal gadget. We're going to define the Langlands dual group. So the Langlands dual group, you can define it by its root data. You can define it by it's a reductive group with its reductive group G, G check, with same W, and it has its maximal torus is the dual to the torus we were given before, and if you can take, and it has the root data which is dual to, so it has roots and co-roots which are dual to those of G. This is a definition, and we want to be a little sure that we're defining not just the Lie algebra. We want to make sure we define the group. We can also make sure to think about its fundamental group. For example, we're going to ask the fundamental group of G check should be the center of G. So this Langlands duality is going to check. That's the dual finite abelian group to the center of G. So this is not a, so what does this formula mean? What it means is that I'm going to exchange simply connected forms with adjoint forms. If my original G was adjoint, my new group will be simply connected. So this is not a terribly enlightening definition, but let's just, maybe I'll write the table of some examples. So GLN is going to be self-dual. So SLN ends being exchanged with PGLN. This is the simply connected and adjoint forms of the same group. If you look at SPN, this gets exchanged with SO to n plus 1. And then you can write down some more examples. Spin to n plus 1 gets exchanged with SPN over Z mod 2, and spin 2n gets exchanged with SO 2n mod Z mod 2. But maybe better to just focus on the types. That type A groups are self-dual, and types B and C get switched, and type D is self-dual. Okay, so this is a definition. This is some definition of a group, and the point is that our double cosets are exactly in bijection with the irreducible representations of this group. Okay, so what can we do with this? Well, one thing we could try to do is move beyond just identifying sets. So remember that these set of double cosets in the classical world, if you look at functions on a finite group, if you look at functions on double cosets, functions on double cosets were in algebra. Yes. Yes, thank you. So I'm going to, everything is going to be, I'm going to stay in the world of complex groups. So my group G and G dual are both going to be complex reductive groups. Thank you. Right, so we want to have an algebra structure. These functions on double cosets should be an algebra. So there are different ways to look at this. So one way to do this is to define this convolution. So maybe this is kind of an aside. Well, so the classical way to do this is to introduce measures. So if you don't want d-modules and all this nonsense, we go to a context where we actually can do integration. And so we can model this space, LG mod LG plus mod LG plus, model this orbits by, I'm going to replace this field, Laurent series, by something, by a kind of nice locally compact field, something I understand. Take a finite field and look at Laurent series in Z over FQ. So just sort of to make my life more concrete, so I'm going to have, I can look at G of FQ Laurent series Z and G of FQ Taylor series in Z, and I take the double cosets. And the reason I'm able to do this is that the combinatorics is exactly the same. The set of orbits are given by some combinatorial data, and you'll get the exact same combinatorial data if I replace C by FQ. So I could just pretend for now that I wasn't interested in C, I was interested in FQ.
You mean the double cosets is the same?
It's the same set of double cosets. Yeah, the combinatorics, the geometry of the situation is exactly the same. So, so I can now put a measure, put Haar measures on these groups, and I could do it. There is a nice integration theory, and I'm going to look at functions, complex valued functions. So let me just let me just give. Yeah. So what am I going to do? I'm going to look at compactly supported, complex valued functions on this set. So there's infinitely many orbits, and I want to take linear combinations of finitely many of them. So I only want to look at functions that have compact support. In other words, are supported on finitely many cosets. And in this setting, I can actually define a convolution, and Satake proved the following theorem. Is this, let me call this H spherical. The spherical Hecke algebra is a commutative. Is a commutative algebra, first of all, which is not at all something I would generally expect, because it's a subalgebra of a group algebra of some big group. And this is not a commutative group. And group algebras don't want to be commutative unless the group is commutative. So I have this subalgebra is commutative, in fact, and it's isomorphic. It's isomorphic to the representation ring of this dual group. Representation ring of the dual group, if you'd like, which is functions on the torus up to Va group, complex valued function. So it's the ring of representations of the dual group, which is what this was suggested. So that it has a basis. The representation ring has generators given by irreducible representations. And those irreducible representations are labeled by these orbits. So this is the classical Satake theorem. But what I'd like to do is I'd like to get at this result in a geometric way. So one thing that's unsatisfactory about this is the definition of G-check was a really kind of ad hoc definition. So the question is, can you understand what G-check is through this theorem?
The G-check that you put on the board there is a complex reductive.
That's right. It's a complex reductive group. That's right. I changed my set of points, but my functions were still complex valued functions. Okay. So now, sorry? This space has nothing complex algebraic about it. But the functions are complex valued functions.
No, I mean, when you write G of FQ of Z or Laurent series,
Yeah.
these are FQZ valued points of G.
Of an algebraic group G, yeah. So G, I'm using the fact that G was actually defined over Z. Right. Okay, so now let me state. So the question is, how do we actually? Where does the Langlands dual group come from? And the point is that this Satake theorem is giving us a hint. It's telling us that the representation ring of this Langlands dual group is captured by this convolution structure on the Grassmannian. So I'm not sure if we have time for this. So, if we knew not just the representation ring, but if we knew the category of representations of the group, we could recover the group itself in a natural way. So there's a very beautiful story called Tanakian theory, or Tanaka duality. And Tanaka duality tells me that if I have a group H, I can consider its category of representations. So my groups and categories, now everything is going to be complex. If I have a complex group, I can look at its category of finite dimensional representations. And now this category has a bunch of structures. This category is a complex linear category because I'm looking at complex valued representations. So maps between them are complex vector spaces.
What kind of a group is H?
So HF for me is going to be again a complex reductive group. I mean this is a very, very general story, but let me just work in this context. So if I have so what kind of thing is rep H? It's a complex linear category. Maps between representations are complex. It's a tensor category. So if I have two representations, V and W, I have a well-defined tensor product associated to V and W. This is a new representation, so this means it's a monoidal, so it's an associative multiplication with various additional properties, because representations of the group have the property that V tensor W is isomorphic, and there's a canonical isomorphism from V tensor W to W tensor V, which switches factor, and in fact, if you do the isomorphism, the switching twice, you get back to the identity. So this is all properties that we know for representations of groups. And there's some constraints on these. So we have this data. There's some constraints that are required to satisfy, and we also need to have a unit for the multiplication, which is the trivial representation. And we need to have some notion of dual vectors, dual representations. And there's a list of constraints that these things satisfy, which you can work out, think what happens to representations of a group. But these are the structures we have on the category of representations. And what Tanaka duality says is that if we have we pay attention to one more bit of data, which we maybe don't tend to focus on that much, there's a natural functor from representations to just complex vector spaces, which is a forgetful functor. So representation is not just a thing, it's a vector space with some structure. So there's a faithful tensor functor, which is just forget that you were a representation, just remember that you're a vector space. And so all of these data define something called a Tanakian category. So a Tanakian category is something that looks like this. It's a linear category with tensor product, which is symmetric and has a faithful functor to vector spaces. And so the beautiful Tanakian reconstruction theorem says that if I give you C a Tanakian category, so if I give you something that has all of this structure, then I can recover a group from which it's the representations. Then you can construct a group, you build a group H, and such that C is naturally equivalent to representations of H. So in other words, what the Tanakian theorem is saying, it's a redefinition of what a group is. A group, instead of the way we usually define a group, to give a group is equivalent to giving such a thing. It's a tensor category with a forgetful map. And if you ask what's the group, group is just automorphisms of the fiber functor. You have a functor, and you look at natural isomorphisms from it to itself. And this is a good exercise to think why that has anything to do with the group in the case of representations. So there's a construction, and the claim is that if I go from H to this category, I get back H. So this is a good way to think of what is a group. So now we know what a group is. We can maybe let me just write down a couple of examples of groups. So that was the wrong thing to erase. Okay, well, what's an example of a group? For example, you could take C to be Z graded vector spaces. So think of graded vector spaces. On vector spaces, you can define a tensor product, the graded tensor product. And there's a forgetful map, which is just forget that it was Z graded. So it has all of this structure. And so this defines a group. And so you have to think which group it is. And the group is going to be the multiplicative group. Or algebraic geometers would write multiplicative group. Representations of the multiplicative group are labeled by integers. Z acts by Z to the n. And that gives you a grading. So any representation is the direct sum of irreducibles, which are just given by an integer. OK, so that's maybe one example. So now that we know what a group is, we can define the Langlands dual group kind of correctly. And this is.
So you mean here finite dimension, Z-graded finite dimension?
Yeah, sorry, everything. Yeah, finite dimensional. Yes. Thank you. Finite dimensional vector spaces. So here, when I have my faithful functor to vec, I want finite dimensional vector spaces. Okay, so what's the group G check? So this is the geometric Satake theorem. And this has a long history. Kind of the strongest form, it's due to Mirkovic and Villanen. And this is based on works of following works of Lustig and Drinfeld and Ginsburg. This has some complicated history. And the geometric Satake theorem is the definition of the Langlands dual group. And what it says is the following, is if I look at my Hecke algebra that we were looking at, so this scary thing we wrote on the board before the break. So I'm going to look at LG plus equivariant D modules on the affine Grassmannian. So I'm going to drop derived categories. I'm just going to have now just abelian categories, not complexes, just D modules. So, or if you'd like, this is the category of D modules on LG mod LG plus, which are invariant under LG plus. So this is a version of my Hecke algebra. Right? So this is my version of the Hecke algebra. It's D modules on these double cosets. And the first part of the theorem says that this is actually an algebra, which is not obvious because I dropped derived. So I need to be sure that I can actually drop derived and still do all the operations I want to do. So first, but in any case, the theorem says that this category is in a natural way a Tanakian category. In other words, the convolution on this, the convolution operation, i.e., first of all, the convolution is commutative. The Hecke structure is actually commutative, and there's a natural fiber functor, and the Tanakian group. So in other words, it defines a group. So this came at this thing by a long, complicated process, but it's actually a group. It's a category with a commutative multiplication, and it has a fiber functor. The fiber functor just takes some total cohomology, so I'll gloss over the details. But this thing defines a group, and the question is, which group is it? Well, with the group, this is the definition of G check, is a reductive group with dual root data. So the real definition of G check, i.e., this is this D modules on this space is rep G check. There's an equivalence of categories compatible with all the structures. But this is where the dual group comes from. So this actually gives you a definition of what the dual group comes from. It's exactly the symmetries of bund G. It's the local symmetries of our space of G bundles. So, sorry? Let me not answer. I mean, the answer is not quite. So the derived version of this statement is not what you would guess. There's a derived version, and it's slightly more subtle. So up to some subtleties, I could have put some derived, but I minimized the lying. That's good. Okay. So, so here it's a statement on abelian categories. So let's say, so maybe just do an example. Essentially, the only example we can just do by hand, which is GL1. And what was our Grassmannian? Our Grassmannian was just Z. Well, Grassmannian mod LG plus is also Z. I mean, so this is my LG mod LG plus mod LG plus. The two actions are the same. It's in a abelian context. So my space is Z. And so what are D modules on Z? It's a discrete set. All I have to give you is a vector space for each component. So D modules on here are exactly Z-graded vector spaces. So this tells you, well, you can guess what the Tanakian structure on here is. It's given by addition of integers. And this tells you that the Tanakian group, GL1 check, is C star, also known as GL1. Okay. So that's the geometric Satake theorem for GL1. So, yeah, right, sorry. So, yeah, that's somewhere I dropped the compact. Yeah, so this is, right, this is compactly supported. Thank you. So on the level of functions, I put compactly supported, and it's important that all these are going to be compactly supported. Thank you. The compactly supported just means I have this discrete collection of orbits, and I want D modules that are supported on finitely many orbits. So we can say I'd like to say some words about the proof of this theorem and how you see this. Right, if you want a fiber functor to vector spaces rather than to some kind of infinite dimensional vector spaces. So you can relax this, and then you would have some kind of inductive limit. You'd have some, so you can look at some bigger category of D modules, and then you'd have some bigger vector spaces. But I mean, that's not completely essential, but you need some restrictions. Well, so these are, hopefully now this statement is just correct. So it turns out that, okay, maybe I should just point out what do these D modules look like, just to give a rough picture, that this is supposed to be the Grassmannian, and it's a union of these finite dimensional orbits. And the point is that these orbits, so orbits were labeled by these lambdas, these co-characters. The claim is that the orbits are all simply connected. And their relative dimension is an even complex dimension. But in particular, the orbits are all simply connected. So if you want a D module that's equivariant for this group, so it's basically translation invariant along this orbit, it's just going to be given by a flat vector bundle on each orbit, and these flat vector bundles in fact are just trivial vector bundles. So for each orbit, all you have is a multiplicity. So the interesting and complicated things are how these orbits are glued together. And there's some very beautiful geometry of how these orbits are glued together. But as I said, the way we want to picture D modules is by flat vector bundles on a stratification, on each stratum you get a flat factor bundle, and those are all holonomic. So in this case, they're forced. The D modules are all forced to be holonomic by the equivariance. So you could add the adjective, but it's not necessary. Okay, so that's the theorem. So what I want to say now. Once you have this theorem, what does it tell you? And it tells you a lot of things. And so it has some very strong consequences. But maybe before I talk about the consequence, the most remarkable fact about this theorem is the most striking thing is that it's commutative. The fact that you have an algebra, that you have convolution is some general nonsense. The fact that it's commutative is sort of something that's surprising and special. There's many points of view to see it, but in some sense, all the best ways to see it are going to be captured by conformal or topological field theory. So we'll see some ways of seeing that. But in some sense, I think the only known proof in some level uses some ideas from field theory. So what's the consequences of this? This tells us that if I look at the derived category of D modules on Bun G, so this is my function space of Bun G, this carries lots of commuting operators. It carries lots of commuting operators. So for any point x and x, and for any v representation of the dual group, I get a functor hxv, which is a functor on this category, Bun G D. So I'm just going to apply. I have this Hecke correspondence. I have this correspondence Hecke x over Bun G. And what I'm going to do is I'm going to stick V. V is a representation of the dual group. That gives me a D module on this Grassmannian, which is equivariant. I'm going to stick it on here. Remember, this was a Grassmannian bundle with structure group LG+. I'm just going to put on that bundle my D module, and I'm going to use it as a functor, as a correspondence. I take a sheaf here, pull it out, tensor with this D module, push it forward. And the point is that all of these operators now are commuted. So it's easy to see that operators at different points commute. But what's remarkable is that the operators at each point commute and, in fact, are given an action of this representations of the dual group. So now, what can you do? You give me a vector space with lots of commuting operators, then you should try to simultaneously diagonalize them. Now we have some harmonic analysis to do. We can try to simultaneously, you can ask, can we simultaneously diagonalize? So in other words, we're going to try to find the analogs of characters on PIC. So I just need to remind you, the way we defined characters on PIC was in terms of the group structure on PIC. But the group structure on PIC was generated by these operations, these z's at every point. So I don't have time to reformulate, but you can reformulate the definition of character in PIC in terms of these operations of taking a line model and modifying it at each point. So what does this tell us? So now we can formulate the geometric Langlands program. The geometric Langlands program is exactly this spectral decomposition. It's going to be spectral decomposition of this commuting family of operators. So how do you decompose? So what is spectral decomposition? Or Fourier transform. We want to take all of these convolution operators and make them into multiplication operators. That's what the Fourier transform does. So we have a space of functions, and we have a lot of convolution operators on it. They all commute. We can try to diagonalize them, means find another space on which all of these act just by multiplication operators. So we want D of Bun G x to be equivalent to something else, some kind of function space, such that these Hecke operators, labeled by points and irreducible representations, become multiplication operators. In other words, just some kind of tensor products. Multiplication means take a sheaf and just tensor it with some vector bundle. Tensor with some vector bundle. So this is the question. Can you do something like this? And the point is that there's an obvious guess. There's a tautological guess of what to do. So if I give you a commutative algebra acting on a space, what do? You take the spectrum of that algebra. Spectrum of the algebra is where that algebra becomes multiplication operators. The algebra is functions on its spectrum. And if you have a module for that algebra, it becomes some kind of sheaf on the spectrum. So we need to find what is the spectrum. So the canonical guess for what to put here is the spectrum of this Hecke algebra, of this tensor product over all x and x of rep of something like this. So it's something like at every point x and x, we have a copy of rep g check. So what does this mean? So what does it mean spectrum in this kind of categorical place? This means some kind of machines. So points of the spectrum. What's a point of the spectrum? It's a machine that turn representations of g check into, well, if I give you a point of the spectrum and a point x and x, I should get a vector space. I should take a representation of g check, and I'd be able to evaluate it and get a vector space. But the question is, how does this depend on the point x and x? So let me make the following claim. What I want is a space of machines that turn flat representations of g check into flat vector bundles on x. Why am I saying these words flat vector bundle? Because I haven't, these points are not discrete set. If I have two nearby points, they kind of talk to each other. It's not like I have a discrete set of operators at every single point. If I wiggle the point a little bit, nothing much will happen. So the spectrum of this thing, maybe I'll have to think about this. You have to stare at this a little bit to be convinced. But the place where, the canonical place where these things become functions, become multiplication operators, is this thing. And what is this thing? This is the moduli space of g check bundles on x. These are moduli, these are flat g check bundles on x. Why are flat g check bundles such machines? This is just a construction of associated vector bundle. If I give you a flat g check bundle, it's something that I can think of in any given representation. So if v, so if p nabla is a flat g check bundle, and v is a representation of g check, I can take the associated vector bundle. I don't know, something like this. This is an associated vector bundle, and it's going to be flat. Flat vector bundle. So that's, or maybe, and if you, in particular, if you also give me a point x and x, I just get a vector space. I get a vector space which is the fiber, which is p, v at x. Okay. So what am I trying to, where am I heading here? What I want to say is, look at this space. So now if you, let's start from this end. Look at this space, g-check bundles with connection, g-check bundles with connection on x. My claim is that if you give an x and x and a v in rep g-check, I can give you a vector bundle. wxv is a vector bundle on this space of connections. And what is this vector bundle? Its fiber, wxv at a particular bundle, is the vector space I had before. Its fiber is given by take your connection, take its associated vector bundle, take its fiber at that point. That's a vector space. So, okay, so this is maybe a little notationally elaborate, but all I'm saying is that on the space of connections, g-check bundles on X, this carries vector bundles WXV, where X is an X and V is in rep G check. And moreover, the claim was that this is the spectrum of the Hecke algebra. So now what's our optimistic? So let's summarize. What's our optimistic hope? We found that if you look at D modules on bund G, we have a bunch of commuting operators on it. We've labeled what these commuting operators are given by. We've calculated something that looks like its spectrum. So your naive hope would be that, our function space, well, our function space is automatically somehow going to live over the spectrum of this algebra of operators. You might hope it somehow has multiplicity 1. So let me now state the geometric Langlands conjecture.
Just a question.
Uh-huh.
Is there a notion of spectrum ring group many objects?
I think so. I think so. Yeah, I haven't seen it written down, but you can define it as some kind of space of fiber functors on this. Well, with a tensor category, not just a ring with. Yeah. Let me not answer that more precisely now. So the geometric Langlands conjecture says that if you look at the space of G bundles on a Riemann surface, and you look at this function space on it, this is a function space that carries a bunch of commuting operators labeled by points and representations of the dual group. The claim is that it should be equivalent to the space of O modules on the spectrum of this Hecke algebra, on which we have these commuting operators which are tensor with these vector bundles. For every point x and representation v, we have a functor which is tensor with this vector bundle. So these are commuting multiplication operators. And the claim is that there's an equivalence of category preserving these operators.
These are derived categories.
These are derived categories. So that's the geometric Langlands conjecture. It should be taken with a little grain of salt. There are various. This is kind of a singular space, and this is kind of a big space, and you need to put some adjectives in front of both sides. And I don't know if those adjectives have been fully worked out yet. Because this is sort of our functions on the spectrum. We want just modules over functions on the spectrum. So there's no flatness in the dependence on this connection. Yeah. Mm-hmm.
Connections, G check X.
Mm-hmm.
And point on that is itself a P with the connection.
Yeah. Okay.
Is there a uniqueness thing? I mean, is there an equivalence of categories consists of two functors.
Right.
In one direction, functor in another direction. Is there some
Yeah, I think
statement that these functors have to satisfy certain properties?
well, the property is that it commutes with these actions, and the point is that if that this action is basically characterizes the space. By kind of Tanakian nonsense, this action really tells you the space. I mean, that's how we derive this picture, is that this commutative algebra knows about this space. What we don't know is whether this module over this commutative algebra really just looks like functions on this space. But the commutative algebra told us that this is the right space. So this is a very rigid requirement. It's not just an equivalence of categories, which is what we wrote yesterday. But the main point about it is it simultaneously diagonalizes all the Hecke operators. So in particular, if you give me P nabla in here, you can look at the skyscraper, O P nabla, skyscraper. This is an object in here. And not only is it an object, well, it's a skyscraper, which means that if I tensor a skyscraper with any vector bundle, I just get a multiple of that skyscraper. So this is an eigensheaf for these operators. If you apply any of these operators to it, you just get a vector space multiple of it. So this conjecture implies that to such a thing, I'm going to assign something called aught P, which is a Hecke eigensheaf, or eigen D module. It's an object here which has the exact same property. So that if I apply, in other words, if I apply Hecke x v to aught P, then I get just a vector space in fact, a specific vector space times alt p. This is the eigenvalue. The eigenvalue is given by the point. So for every eigenvalue is given by this local system. So the geometric Langlands conjecture says that these Hecke operators can be simultaneously diagonalized. So in other words, there's a basis for this function space given by eigensheaves. Those eigensheaves exactly are labeled by points here. So it's a Fourier transform that takes points to these. So these are our analogs of characters in the case of the Picard group.
Does it make any sense to take the K theory of both these categories? If that makes sense?
Sure.
And then what? Get an isomorphism of the Abelian groups?
Well, you should get an isomorphism of Abelian groups with module.
With the modular.
Yeah.
With the
Yeah. Okay, so I'm out of time. I'm going to leave you with a picture. Well, maybe I won't leave you with a picture. So the interesting question now that's left is, why is this commutative? And I'll just make a kind of hand gesture. And the basic picture why it's commutative is because we have a lot of room. And instead of thinking of all these operators stacked up at one point, we can think of putting one operator at one point on the Riemann surface, another operator at another point, and colliding them. And this beautiful picture developed by Drinfeld says that this convolution operator on the Hecke algebra is actually coming from collisions of points. I can think of putting one operator at one point, doing a modification here, doing a modification there, and their composition just comes from operator product expansion. So there's a beautiful formalism coming from conformal field theory, which is a formalism for collisions of operators sitting at points, also known as vertex algebras. And that's why this thing is commutative, because if they're living at different points, they can kind of move around each other. There's lots of room. You can, instead of going like this, you can go like that. So sorry for the gestures. But that'll appear tomorrow. OK, thank you.